string theory. As we have been doing so far in these lectures, we focus on the closed string. In a few lectures, we'll start talking about things like open strings and non-open strings and so on. But we first want to just understand all we can about the closed string before we come on. Okay, so the aim of today's lecture is to calculate 3 and 4 point functions of the tachyon closed string theory. And in the next lecture, we will also do some calculations with the more interesting but slightly more technically involved states, namely the ground and the delta construct. Okay, so now what do we need? So we have this lovely general formula for sketching applications in string theory. The general formula is written in terms of an integral over correlation functions in conformal field. So with the elements we need in order to calculate these correlation functions, in order to implement these scattering amplitudes are correlation functions of conformal field. Okay, so much of today's lecture will be devoted to computation of correlation functions of the kinds of operators we're interested in conformal field theory. And the conformal field theories of interest are both free theories, the free scalar field, say free BC-CFT. So it's very simple, but anyway we have to do it. Okay, so let's first start with the scalar field. Since this is the first time we're doing it, I'm going to give you 2 or 3 different methods of doing these calculations of different levels of rigor. Okay, all methods will eventually give the same answer, but just so that we do it in many ways and you can see all the similarities. Okay, so what's going on? So our action here is equal to minus 1 by 4. So it's equal to, so we're calculating dx mu e to the power minus s, where s should be equal to 1 by 4 pi alpha prime d to sigma square root g del alpha x del beta x g alpha. Okay. Now, before getting into detailed and really logically completely satisfactory calculations, I'm going to first give you a rough and ready calculation. Okay? More or less because when you do your calculations in real life, that's all you'll ever do. Once you've seen how all the subtleties cancel out with each other. It's not the way a textbook would present it, but it's not the way a good textbook would present it, but it's what you'll actually do. So let's see. So the first thing we need to do is to say that, we should be doing the calculation of the sphere. That's we're interested in three identities. But the sphere is conformally equivalent to the plane. So not quite right. That's the point of infinity where you have to do something funny and so on. Let's begin with that. Okay, so we'll do this calculation of the plane. So G is set to the flat metric of the plane. Okay, so S is equal to d to sigma 1 by 4 pi alpha prime d to sigma del alpha x where you're contracting the derivatives to the flat metric. Okay, now what amplitudes do we want to compute? So let's start by saying what we want to do is to compute e to the power I k dot x, k1 is 1 at sigma 1 by k2 x dot x at sigma 2 by kn dot x at sigma 2. Okay? These are the tachyon vertex operators, setting identity times the momentum. We will soon turn to oscillators as well. Let's take the first one.
When you're taking everything is signature?
You did. Everything is unique. We've analytically continued so that we're completely unique in space. Okay. So now, how do we do this calculation? Well, here we use the fact that, the fact that it's true of any Gaussian integral, that if you have, suppose you've got some Gaussian integral in the x-axis, and you want to do a calculation like ji xi, exponential of ji xi. There's a general formula for this expectation value to the Gaussian measure, and the general formula is just e to the power ji jj by 2 xi xj. The xi xj is the 2-point function of xi xj in this this integral. Again, think of this as, we could derive this in 2 minutes if anyone wanted, but I'm not planning to unless somebody's speaking uncomfortable. Okay, yeah, you could put an arbitrary mij xi xj minus mij xi xj by 2 because the integral, do the integral by completing the square, and compare it to the two-point function given results. Okay, a good way to remember the factor by the way is to expand this out to second order. See, if you expand this out to second order, you get 1 plus ji xi plus ji xi times jj j. And this is of course summed over ij. Okay? ji xi times jj xj by 2. And then if you take expectation values on both sides, 1 is 1, this is 0. And this gives you the first term, the expansion. So if you remember that of this form, the factor is easily derived by an expansion. Okay? Good. So now let's go ahead. So this is what we want to do. You see, it's of this expectation value is of the form of interest. Okay? So the answer then is simply e to the power. Now this is minus because I squared is minus 1. Then sum over I and j, ai dot aj into expectation value of well, to be more precise, this is ki alpha kj beta, the expectation value of x alpha sigma 1 of x beta sigma 2. But as we know, it's expected as a 2. Okay. But what do we know about this expectation value? Sigma I. Okay. But what do we know about that expectation value? Using that expectation value we've already computed. We computed in an early class. I'll just remind you how we did that. We did that by saying, consider the integral dx mu, then put an explicit insertion of x mu. Okay? And e to the power minus s, and take this action and functionally differentiate it with respect to x mu. Because it's an integral of a total derivative, we get 0. But that 0 has 2 terms. There's one term which is the expectation value of delta of, so suppose this is at sigma 1 and we differentiate with respect to sigma 2. So we get delta of sigma 1 minus sigma 2. And the second term, we pull down a functional derivative with respect to the action, x of the action. That gives us a plus del square. Plus because we integrate by parts, which cancels the minus. So you get a plus, and there's a factor of 2 because the 2 x's are which that. 1 by 2 pi alpha prime del squared x of sigma 2. So this is equal to 0. Okay? And in this term, sorry, it's also the x of sigma. Okay. So that tells us that the 2-point function obeys the differential equation del squared by 2 pi alpha prime on x of sigma 1, x of sigma 2 is equal to minus delta of sigma 1, 2. And remembering that log r, that the derivative of log r, d by dr of log r, is equal to 1 by r. And then doing the surface integral of this, we get 2 pi. It's 2 pi r times. Think of this as normal vector. We say that log r has del squared equals, so log r, del squared of log r is 2 pi times delta of delta 2. Okay? So now what's the right answer? So the right answer is x of sigma 1, x of sigma 2 is equal to minus alpha prime by 2 log of r squared, which is mod z1 minus z2. of x minus z. If this is x, okay, fine. So we've got this 2-point function in our hands now. It's the same thing we derived before, just reminding you. Right? Okay, so now let's go. So all we have to do is plug in this 2-point function. Okay, of course at this point you could ask, how do we know this is the right function? Why can't we add any 0 mode del square to this function? Well, it sounds right, it's translationally invariant, it maintains the symmetry. Basically, it's a unique translationally invariant solution to that equation for the plane. All other solutions will blow up somewhere, blah, blah, blah. We'll come to such questions in more detail in 10 minutes. Okay? But this is, sounds like a very reasonable answer. Okay? So now let's move on. Okay, so let's just use this answer and apply it. So, of course, if we put the mu nu indices here, we get mu nu and we get delta mu nu as well. Okay? So, now if we apply it, what do we get? We get e to the power minus sum over I and j, ki dot kj over 2. And then we have minus from here, so we get alpha prime by 4 ln of zi minus zj the whole square. Okay? Now this sum has two kinds of terms. The terms where I is equal to j, the terms where I is not equal to j. So breaking this up into the two terms, we get e to the power plus alpha prime by 4 sum over I ki dot ki ln of zi minus zi the whole thing squared. Okay? Times, the other stuff is just zij, which zij is zi minus zj, to the power ki dot kj by 2, the whole thing squared. Well, that's right. I less than j. Product over place. Okay. Now, we're basically done, except for this business. Except for this business, because this thing gives us something defined. Now, what's the problem here? The problem is, of course, that we're looking at an composite operator. And we're going to renormalize the composite operator before computing its correlation functions. We're going to come back to this in 10 minutes. But at the first pass, you say, well, suppose we somehow renormalize it so that we don't allow self-contradictions. Okay? Then we wouldn't get any of these terms. These terms all come from x's contracting with x's at the same point. We don't allow self-contractions, we normal order or something like that. We won't get any of these terms, so this must, once we do the correct renormalization, this must be it. This is almost right. As we'll do this properly. Okay? Okay. This is our first pass. Is this clear? Okay? So, and basically this is correct. This is basically correct. Have I got some alpha primes here? Okay, this will really be all we need to actually calculations. Okay, let's continue with our rough and ready method. Okay, for computing correlation functions of the other kinds of things we need. For instance, suppose attached to some of these e to the power I kx's, we also had derivatives of x. Those are the other kinds of vertex operators in there. Will be interesting. Right? So now how do we do that calculation? Well, in order to do that calculation, you use another nice property of Gaussian integrals. Okay? And the other nice property of Gaussian integrals is this. That suppose you've got something down in the denominator. You want to compute expectation values of various objects down in the denominator. And you've got these other linear terms of the exponential. Then, in order to evaluate the expectation values of such an integral, the first thing you do is to substitute whatever is in the denominator according to the solution to its equation of motion. We'll do this in more detail. Sorry, okay, so let me just write the formula. Can I clear this? Okay. Okay, so suppose we wanted to compute e to the power minus ki xi, okay, or plus ki xi, okay, just in any Gaussian integral, times x product over m xn. We're going to compute this. That's what I mean down in the denominator. Just that. I mean downstairs, not upstairs. Sorry. Okay. Now if you wanted to compute this, you see, basically imagine how you would do this calculation. The first thing you would do is to make this a complete square. Okay? And then you would compute expectation values in the complete square. But it becomes a complete square in new variables. Okay? So you would write these xm's in terms of the new variables. So when you did that calculation, you would have the xm written as whatever you get from the solution to the equation of motion of the stuff that's upstairs, plus something else, okay? And the something else can then be contracted, interfering with e to the power kx. Let me give you an example of this. A trivial example. Just to make sure you understand what I'm saying. Suppose we wanted to compute e to the power minus.
Apart from a factor.
No, this is totally exact. Oh, you mean like the determinant?
Maybe a factor like jxi, right? Which is like
jxi. Sorry, what's j?
Like, okay, the x's will be shifted into some y plus something.
Yes.
Okay. Now for we are only doing the integrals over the something, then eventually calculating the expectation value of only those things are in the classical.
Let me give you this example a little here. So suppose we have e to the power minus x square by 2, okay, plus alpha times x is 1 by 2. And I wanted to compute expectation value of x squared. So let's first do it the way we would actually do it and then interpret this. So what would we do? We'd say, well, this I can rewrite as e to the power minus x minus a, the whole thing squared by 2, plus a squared by 2.
You get the difference.
Yeah. So we're going to get whatever we would have got otherwise into whatever we got. Okay, so let's go through this example and then we'll see. Okay, right. So we get this, and have I got the signs right? Probably I got the signs wrong. The minus is right. Okay? And then we would have had, and we have this thing has a with a minus. Yeah, sorry. Yeah. Okay? And then we have x squared, which I'll write as x minus a plus a, the whole thing squared. Okay? Now, x minus a, so now the answer is e to the power plus a squared by 2, which is the answer we would have had without any of these insertions. Okay? Times the contraction of x of y squared plus a squared, y plus a the whole thing squared, in e to the power minus y squared by 2. Okay? So now this new calculation involves, this new calculation still involves calculating correlation functions, but involves calculating correlation functions without this exponential deformation. Okay? So now, here you can just do weak contractions. Just replace things by weak contractions. This is another property we have about Gaussian integrals in the variable y. So what's the general rule? I worked out one variable, it's totally general. What's the general rule? If you've got a Gaussian integral with exponentials and stuff downstairs, then firstly you get the answer for just the exponentials. That will multiply that. Secondly, you replace the variable downstairs by what that variable is on the solution to the equations of motion. You see, what is the equation of motion here? The equation of motion was x is equal to a. Okay? So you replace that by a plus something else. That something else is a fluctuation variable, this y, which then will be contracted according to usual quick contraction rules. Okay? So that's the general rule for doing a Gaussian integrals with exponentials upstairs and stuff downstairs. For the stuff downstairs, replace it by what you get from the equation of motion plus a fluctuation variable which you contract by quick contraction. Finally. Not clear? Okay? So now let's implement that in the situation of equals to us. Okay, so suppose we were interested in some number of, this works for any numbers of derivatives, effects, just for concrete results in first derivatives. Okay, so del x at sigma, sigma a, sigma tilde 1, del x at sigma tilde 2, and so on. And then e to the power I k x at sigma 1, e to the power I k x k1 is km x at sigma. We wanted this object. So the first thing we're supposed to do is to take the answer we would have got from here, which is this is producted over pairs. The pairs of I and J. So I should take the product. I less than J, Z I J, alpha prime, Ki and Kj. And then I'm supposed to look at what these del x's would become on solutions to the equations of motion. So what are the equations of motion? That's a classical part. So what are the equations of motion? The equations of motion were 1 by 4 pi, no, by 2 pi, it's differences, 2 pi alpha prime del square x is equal to what? Plus I k1 km dot km mu delta of sigma minus sigma m sigma is equal to 0. Okay, but we already know how to solve these equations. The answer is simply, let me get the i's and minuses right. It's I alpha prime and then with the minus log of sigma minus sigma prime. What if I put a square here? Okay, sigma minus sigma m and sum over m. The x of sigma, x mu of sigma, and there's a k mu of course. K mu m. Let me write it again. It's here. It's correct formula. Minus alpha prime by 2 sum over m k mu m log of sigma minus sigma m square. And I think I understand. Okay, so this is the solution for it. So if we want to del x mu now, just what this object is on the solution to the equation of motion, we differentiate this. So what do we get? to get del x mu. Yes. So we get del x mu is equal at sigma tilde dot k is equal to minus I by alpha prime by 2 k mu m by z minus z. Check these functions. That's right. Minus I alpha prime by 2, perfect. Okay, so then according to our general rules, every time we have one of these del x mu's, we replace this del x mu by del x mu plus, we can call it q of sigma 1 tilde. And the q's have the proper, or maybe it's better to call it del little x mu of sigma 1 tilde. Okay, so we can replace this by this thing minus I. So by this, we can replace. So every time we apply a del x mu, so del x of sigma j tilde is replaced by minus I by alpha prime by 2 k mu m over z minus zm sum over m. Okay, and then plus del little x of sigma 1 tilde. And the rules, now the correlation function of del little x is just contract them according to Wick contractions, where little x has the usual 2-point function. The 2-point function we derived at the beginning of the class. Okay, so you can contract 2 of them, 4 of them, in all possible Wick ways, using the 2-point function we derived, so minus alpha prime by 2 log of mod z squared for the contractions of the x. Of course, if we only have single dels, this effective contraction will take the log and make it a 1 by z squared, because you have 2 parameters. Okay, so we won't give the rule in more detail than this. The prescription is replace every insertion of del x by this, and then do the contractions of the little x's, and you get the answer. You could try to write down a general formula for that, but it's not worth it. In any case, you just do the contractions. Okay, is this clear? So, we've finished method 1, our rough and ready method for computing correlators. There's just one thing left to say about this, and that is that you see, and the other methods will make this, better methods will make this much clearer. But that is that in doing this path integral over x's, in particular you do the path integral over the 0 mode of x. The path integral over the part of x that is constant everywhere. Okay? This path integral will, apart from everything we've talked about here, enforce a delta function for the various momenta. Because how does the 0 mode of x? So let's take x and shift x to x plus constant. What comes behind that constant? The sum over all ki's. The sum over all km's appears in the exponent. And you're doing the integral over that constant, you have a delta function of sum over all k's. Okay? So when you do this in any correct way, you will also find, in addition to all of this, a delta function that imposes momentum conservation. That there has to be a delta function of this sort is clear from many points of view. You see, x goes to x plus constant is a symmetric theorem. So if you take any of these correlation functions and you send x to x plus constant, you get that this correlation function is equal to the same correlation function times e to the power I sum over ki times that constant. The only way that correlator can then not be 0 is if that sum over ki is 0. Okay. So the better be that the sum is proportional to the delta function. Delta function that imposes momentum conservation. Is this clear? So we've seen all the main features of the theory. Basically what we're doing is a Gaussian integral. We get a momentum conservation delta function from the zero mode. We get these powers Zij to powers from exponents, and we get these classical pieces plus width contractions from other insertions downstairs in the integral. Okay, but now since since this is the basis of everything we're going to be doing later on, and since this is a course, we want to do this in a two, three different ways, where we understand some of the rough things we've done a little later. Okay, so why don't we sweat under the carpet here? The first thing that we sweat under the carpet is that we're actually looking at correlation functions in a sphere. Okay, we're actually looking at correlation functions in a sphere, not a plane. Okay, so does that correct things somehow? So now I'm going to follow Bolshinsky and give you two different methods to get this answer, each of which has its own nice things and each of which will help you understand certain things about the calculation. The first method we'll use is to appeal to general properties of conformal field. Okay, we'll try to do the answer, we'll try to do the calculation in conformal field theory, using the techniques of conformal field theory, but remembering that we're running on the sphere. Okay? Now how are we actually dealing with the sphere? We'll deal with it the way we did last time in yesterday's class. Remember what we said in last time's class? What we said was that we can cover the sphere by two patches, the Z plane and the Z patch and the U patch. Now, remember that we're dealing with a theory which we have gauged by diffeomorphisms and Weyl transformations. Okay? So, if you have some field on one patch and where it overlaps with the other patch, it's equal to the field of the other patch after the appropriate diffeomorphism plus Weyl transformation. Okay? So firstly, the two metrics in the two patches have to agree after diffeomorphism plus Weyl transformation. But the way we did it was to make these two things conformally equivalent. Just analytic functions of each other. So that was guaranteed. Because the conformal transformation changes the metric by an overall factor, which you can then observe by Weyl transformation. And then we said if we knew how every field in question transformed under diffeomorphism plus Weyl transformation, then we know how to transform fields in one patch to fields in the other. We know how they transform under both. Now, in every case that we looked at, last time we were looking at the B and C system. Remember, the BC system was neutral under Weyl transformation. They were Weyling there. So the transformation under the diffeomorphism plus Weyl transformation that takes you from one space to the other is simply the transformation under diffeomorphisms. Okay? And that's the principle we use to determine, if you remember, how many zero modes to C there were and how many zero modes to B there were. We're just transforming them from the Z patch to the U patch by diffeomorphisms. There's also the Weyl transformation, but we threw that away because these things were neutral. Okay? Similarly, in the X field is neutral under Weyl transformations. More precisely, the things that we will actually use is that del X transforms only under diffeomorphisms. Again, it's a dimension 1 operator, and all of its transformation properties are what you get by the transformation properties of del. Okay, so now let's use this basic idea to try to see if we can pin down these correlation functions from another point of view. What I'm going to do is a little convoluted, yeah? It's a little tricky. This is sort of first principles way. It's a little tricky, but it's worth doing just to see how the formula is. Finally, I'll give you another more serious path in technical. Okay, so what are we going to do? Well, to start with, we need to see if we can compute del x of sigma 1, sigma 2 using conformity theory techniques. Okay? So, what do we know? We know all the singularities. We know all the singularities of del x because we know it's OP. Okay? So we know that from the OP, since we had xx was minus alpha prime by 2. Right, so we get minus alpha prime by 2 1 by z1 minus z2 the whole thing squared. We know that this is the only singular term. Okay? So, to this we can add any function of z1 and z2. To this we can add any function of z1 and z2 that is analytic. Okay? But this correlation function has to be completely well defined everywhere in the sphere. Okay? So let's see. Suppose we have del x. Okay? Del z of x. Let's see what it becomes in terms of del u. So we would let's say game we played last class. Okay? So we have u is equal to 1 by z. So we get del u of z is equal to minus del z of x times dz by du, which is equal to minus plus del z of x times dz by du is what? It's z is 1 by u, so it's minus 1 by u squared, which is equal to z squared, so minus z squared times z. Okay? So in order that del u of x be well defined and u equals 0, del z of x, okay, has to fall off at least as fast as 1 by z squared, at least as fast as 1 by z squared at infinity. We see that the singular term does that very nicely. Falls off as fast as 1. But suppose you have an analytic piece that also falls off as fast as 1 by z squared. No such term exists. There's no function that's analytic according to the z plane, and when it goes at infinity, falls off as fast as 1 by z squared. Okay? So this analytic part of this thing here, this possible analytic contribution here, must be equal to 0. Okay? So we find that this is equal to this with no further application. You see the vertex operators, remember what the vertex operators are. Yeah. The vertex operators are derivatives of fields times each part of x. Okay? And that's what we want to calculate. Okay? Also just at the technical level, derivatives of fields are have good conformal good conformal properties. But anyway, so the physical reason is the vertex operator. Okay, great. Now this was nice, but so far, and this could easily be generalized to products of arbitrary numbers of del x's without any e to the pi x's. I'll leave that as an exercise for you to try. Basically, you get all possible ring contractions and anything else that you will try to add. Anything else you will try to add will have to be analytic and will be set to 0 by similar sort of argument. Okay? You see, by the way, it sounds trivial what we're doing, but it's not so trivial. See, we're accounting for we're doing it correctly, accounting for the fact we're on the sphere. We're using the fact that the OP is correct in any local batch. And then we're allowing the fact that we're actually on the sphere, and still we're getting this result.
If being a plane, then I could add.
And you could add exactly. You could add some analytic pieces. Exactly. And then you have to basically you have to have the right boundary conditions at infinity. The boundary conditions we have at infinity is that we conformally at the sphere, and that rules out anything else. That's basically the boundary. Okay, now let me use a method that's a little more clever to try and use the same kind of reasoning to get the correlation functions of insertions of del x along with e to the pi ikx's. Now this is a little tricky because x itself does not quite factorize into left and right numbers. del x is purely left. But e to the power ikx does not quite factorize into left and right numbers. Because of that, we're going to use a slightly indirect method. Okay. Let's just see what we do. Okay, all of this is slightly trickery, but okay, let's go to see it. Okay, the method goes as follows. Suppose we were interested in del x times e to the power I k1 x1 e to the power I kn x. Okay, and by the exponential operator insertions, we will always understand conformal normal or anything in whatever. So everything's totally well defined. Okay, now okay. So now suppose I was interested in this object. So let's say that this is the point sigma. This is at sigma 1. This is at sigma n. Okay. Now, the first thing I can do is easily calculate all the terms in this expansion that are singular in sigma. Okay? By looking at the OPE of this operator of nature is. Okay? So let's do that as an exercise. Let's look at del x mu of sigma with e to the power I k, let's say 1 x k1 mu x mu of sigma 1, and let's compute all singular pieces in sub E. Okay, so one way to do it is to expand the exponential del x mu sigma sum over n I k mu x mu sigma to the power m by n factorial. And then all singularities in the OP are given by contractions. Okay, so we get minus I k mu minus I k mu. The log goes away, alpha prime plus minus by 2 z minus zi. This is z1 we get the factor of m because we have n possible ways in which to contract. That cancels the m factorial, and this just becomes e to the power I k. Okay, so I'm claiming that, so let me just write down the final result. I'm saying that del x mu of sigma times e to the power I k mu of x mu of sigma, the only singular piece in this OPE is equal to I k mu alpha prime by 2 z minus z1, this is sigma 1, e to the power of I k mu x mu of sigma. And you see how we got it, right? We took this exponential, expanded it, looked at the singularities term by term, and then resummed what was repeated. Is it clear when we contracted this with the guy with the m? Yeah, we get, there are n such terms, we get a factor of n, which cancels this n factorial to make it an n minus 1 factorial. So what you have left is x mu to the power n minus 1 by n minus 1 factorial, so that re-exponentiates. But there's an extra factor of I k mu, which you have to pull out. That's this. And here we got alpha prime by 2, and then of log, as you said. Okay? Fine. So, okay, let's hurry up with this. Okay. So, now if you look at the singularities with the other variables, you get the same kind of thing. So the singular part of the OP, the thing that is singular in the OP is, so this thing includes a piece that is sum over m I k mu over 2 z minus z m k mu m over 2 z minus z m alpha prime times e to the power times expectation value of e to the power I k m sigma m. Okay? And anything else must be analytic in Z. Anything else must be analytic in Z. But we've just seen that we just did it, that the function, if it's going to be well defined in the U plane, del Z has to behave like 1 by Z squared at infinity. Okay? Now you might first be a little confused because of at the poles bit, the singularities we're getting do not behave like 1 by Z squared at infinity. So how does that work? Well, it can only work if you correct the coefficient of 1 over Z and the part that's that multiplies it is 0. But you see the coefficient of 1 over Z is simply sum over the k mu's. So the first thing we conclude is that we have momentum conservation. That the only way this amplitude can be non-zero, that this thing here can be non-zero, is if the sum of the k mu's vanishes. Okay? Once we ensure that this thing does indeed go like 1 over Z squared at infinity. Is this clear? You can write down a Taylor series expansion for the Z infinity. The leading term is 1 over Z, with some coefficient being sum of k mu's. Next term is 1 over Z squared, and so on. So that term is fine, but this term here has to be analytic. It has to go like 1 over Z squared at infinity. There's no such term in zero. So, we've concluded that this correlation function, we haven't been able to calculate it. But what we have been able to do is to relate it to the correlation function without the insertion of a del x. So we've got a nice equation that relates the correlation function with the del x inserted and the correlation function without the del x inserted. Okay? Now how do we proceed? Now what I want to do is to turn this equation into a differential equation for this correlation. And the way I do that is to notice that if I take this object, okay, if I take this object and multiply it by kb, okay, so if I take this object and multiply it by kb, then the first piece, okay, so let me say this, okay. Suppose I was interested in del x mu, k mu, k1 mu times e to the power I, k1 of x. So this is at sigma, this is sigma. We've just computed the most singular part of the OP. But what remains once you remove the OP? What remains once you remove the OP is simply, so we got the singular piece which we just computed, plus normal order of k mu del x mu e to the power I k1 x mu. That's the same. And now, if we want to compute all the remaining terms of the OP, all we have to do is to Taylor series expand. So to write sigma as sigma 1 plus sigma 1 minus sigma, plus sigma minus sigma 1. And Taylor series expand this in sigma minus. The order 0 term, the term that is neither singular nor zero as x goes to x1, is simply k mu times del x mu at sigma 1 That's equal to pi k1 x mu and sigma 1. Everything is within the normal order system. So multiply things at the same point is no problem. Okay?
So we are looking at this kind of correlation functions which you are writing as a similar power plus.
And the moment I just started looking at this operator, suppose I look at this operator like this operator. Remember, in the first few lectures we understood how to compute such OPs. Okay? All we had to do was to use Wick's theorem to normalize. Okay? So you get a singular part plus whatever remains is the product of these two things within the normal order. That's sign. So that's what I've done. You get singular piece plus whatever remains within the normal order. Okay? This is still at point sigma, this is still at point sigma 1. Now if you wanted to generate the full OP, not just the singular term, but every term of the OP, now it's totally trivial. All you have to do is data expand. Because there are no singularities anymore. There's just 9 data expansions just to calculate. Okay? So all you have to do is data expand, write sigma as sigma 1 plus sigma minus sigma 1 and expand that sigma minus sigma. Okay? So the lowest term in that data expansion is just sigma is equal to sigma. Okay? So the lowest term of the sigma in this. So what we get is something singular plus this plus order sigma minus sigma. But now this piece here is simply del of e to the power I k1 x mu of sigma 1. Okay. If I put an I here. So let me do it with an I. And then take the derivative. Derivative of this object is I k1 and derivative of x mu. Is this clear? So, what this allows you to do is to say that, well, suppose, okay, so what have we done? Well, our aim is to compute this correlation. Okay, that's our aim. So what we get is the following relationship. We say that, well, what we have is that the derivative, what we have is the following claim. We have that the okay, what we've got is the following claim. We've got that the derivative with respect to sigma 1 of the thing we want to calculate, the thing we want to calculate is this, right? Okay, is equal to the order 1 part of the OP, the term that is order 1, when you take sigma to sigma 1, in the sigma minus sigma 1 expansion. Okay? Is this clear? Let me say it again. This quantity, the derivative of the thing we're interested in with respect to sigma 1 is simply that part of this expectation value that when you take express it as an analytic function in sigma minus sigma 1 is the constant piece of it. Is this clear? Okay? Take that up. But now this is useful since we know this answer. We've computed this answer here. Okay? So, you see, what does this answer have? It has a pole in sigma minus sigma 1 that comes from z minus z1. But it also has all the other pieces which was z minus zm, where m was not equal to 1. Okay? So, those are the order 1 part of that correlator as far as the expansion. So, what are we supposed to do? We're supposed to set z is equal to sigma 1. So, we're supposed to set z is equal to sigma 1 plus epsilon, and there will be a piece that's 1 over epsilon, there's a piece that's constant, and then there are the positive powers of epsilon. We're supposed to isolate the coefficient of the piece that is constant. Okay? The term that was just z minus z1 was simply 1 over epsilon. The term that was z minus zj, from j not equal to 1, was z1 minus zj plus epsilon. Expansion of the epsilon gives you the higher order terms, we don't care about this. Okay? So we concluded that del with respect to sigma 1, what we want is equal to I alpha prime by 2 k sum m not equal to 1 m over z1 minus zm. This is what we call z1. Times what we want. Is this clear? Of course, we also have a similar differential equation with respect to every other variable. Because we chose one at random, we could have chosen the variable k, epsilon k. What's the solution to this equation? The solution to this equation is simply that this completely determines z1 dependence of thing. It's simply that we have f is equal to z1 but zij to the power I alpha prime by 2 and I'm sorry, I should have also, you see, we needed to multiply by, sorry, let's get this straight. We needed to multiply by I k1 in order for this to be true. So we should multiply this by I k1. So okay, I may have got a minus sign off. I'm getting k1 dot km alpha prime by 2, and the multiplication I'm getting a minus sign. I've done something wrong. But you see, this was exactly, if you forgive me the minus sign, this was exactly the answer we had. We've done it with respect to the analytic part, but there's similar dependence on the anti-analytic part. So the zij mod squared to the power alpha prime by 2 ki dot kj. This was the correct answer. Somewhere I lost a minus sign. I'm going to ask you to forgive me that. I can check the Kulczynski to see what it's saying. Yeah, in his differential equation, he had this equation with a plus. Okay, I'm going to ask you to track down that minus sign. Do it carefully. Sorry, I messed up the minus sign, but we did it carefully. We get it. Okay. Let's see. Have we got the OP right?
Taking derivative means multiplying with another ik1. That gives a minus k1.
Yeah.
There is a 1 by z. That restores it to positive sign.
Yeah. But actually, Kulczynski's OP just had a minus sign here. He had, sorry, his relationship here had this sign minus.
I think that is minus.
That's minus. Sorry, I messed up in calculating that. I don't know why I messed up, but I messed up somehow. Oh, the minus there is just the minus from the minus of the 2-point function. The 2-point function is minus alpha prime. I think we ignore that in calculation. We can calculate this OPE again. You see, what are we going to get? We're going to get a factor of I times k mu. That's left behind.
Basically, the expectation value of x.
That's right. That's right. Times the derivative of minus of alpha prime by 2 times log. Okay, so that's the minus. Sorry. Okay, we got minus here, we got a minus here, and now everyone's happy. That's the answer. Okay, so you see what a slick method this was. Though it would be hard to think of yourself perhaps. But you see, using only conformal field theory methods, never calculating a path integral in your life, okay? Using only conformal field theory methods and similarities from the OPE, we completely managed to reconstruct all the correlation functions that will be of interest. It's pretty cool. Okay? And this method, if you think about it, unlike previous methods, is totally satisfactory. It's completely correct. Okay, but now there's one more way I hope this is really going on, but still. So there's one more way I wanted to introduce you to calculating this. That's to do the path integral. Once we start doing the path integral, then we do it in a slipshod way. That's unsatisfying. Hey, you want to do it in the right way. Okay, so let's see how do we do the path integral correctly. Perhaps in view of time, I'll just sketch the method and ask you to read it first. Let me give you all the logic. Okay. You see, there are many things that one needs to do in order to do it correctly. Okay, let me just sketch it. You see, suppose we were on some surface, an arbitrary surface. At the moment we're interested in sphere. Suppose we're on an arbitrary surface. The thing we can do is to take any function x mu and expand it in an eigenbasis of the operator x. Now, a scalar function always has a zero eigen of n square, namely the constant scalar function. That is always a zero eigen. Okay? So there's always x0 plus let's say alpha 0 plus alpha m xm. And let's say that del squared on x0 is equal to 0, this is the constant mode, and del squared on xm is equal to omega m. That's the square minus omega squared. Yeah, minus omega m squared. Okay, now what we can do is to take the action that is of interest to us. We can take the action that's of interest to us, namely square root g.
And this omega m
Will be
some sort.
Will be some sort. We're not going to say much about it.
They might not be proportional to m.
No, some way. Okay, square root g del alpha x mu del alpha x mu. Okay, we'll contract now with the real metric. And by integrating by parts, you can rewrite this action here as okay. You also choose these xm's to be normalized. Choose these xm's to be normalized in the sense that square root gx m1 squared by x n is equal to that. Hermitian operator, so we can always do that. Hermitian operator with respect to this norm. So we can always do that.
This is opposite. Without any omega.
Without any omega. It's just the norm of the eigenfunction should be normalized. Okay? So now, once you do this, you take this, integrate by parts, make this a del square. And you see, of course, that what this becomes is minus, so this thing is equal to minus sum over m, omega m squared. Okay, now it becomes actually plus because omega m squared is minus, plus omega m squared times alpha squared. Okay? So this action here that you write down, this action here you write down is written purely in terms of the non-zero modes, of course. Okay. Then the next thing you do is to ask, what is the kappa? Suppose we were trying to compute e to the power j of sigma x of sigma expectation value in this manner.
So this alpha, I mean, it is different from what we usually use as alpha.
Yeah, this is just a, well, it's not.
When we have e to the power I, usually normalize it with omega.
That's right. This, in that sense, this is certainly good. We're just normalizing it the usual norm. You know, this method is very abstract and it works in an arbitrary manifold, not just the sphere. Okay, let me quickly run through this. It's not so interesting. Just so that you can do it properly. You see, now the next thing you do is that suppose you want to compute the expectation value of something like this. You substitute x in terms of x's. Okay? And then define Jm to be the integral of j of sigma with xm. Okay? So then what this becomes is alpha mjm. Okay? Plus alpha 0 x. This runs over all non-zero modes, this is the zero. Okay, now if you do the integral, you see, the key point is that the manifolds we're dealing with are discrete. Yeah. The manifolds we're dealing with are compact, so the spectrum of del square is discrete. So all of these things are discrete modes. Yes, there's no continuum like it seems when you're doing the problem on the plane. Once you do it really in the proper way. Okay, so now we do. So if you want to compute this correlation function, all you have to do is to complete the squares. Okay, so you get whatever you get from the non-zero modes, and you get clearly now a delta function for J0 from the zero modes. Right, because the only place where alpha 0 appears is in this insertion. Okay, so we put in I, for instance. Okay?
Because all the insertions are there.
Because all other insertions are in X, that's right. But if we do try, suppose we just try to compute this kind of stuff. Okay, now the next thing you can do is to write down exactly what you get from these JNs. So what do you get? And I'm going to rewrite this eventually in terms of a Green's function. Right? And it's not a formal nonsense, okay, by the way. I mean, it's okay, but not just worth the time. But okay, so let me just finish. Let me just finish on this. Okay, so what do you get? So what do we get is Jm times Jm. Now you're completing the square. There was an omega m squared. Yeah, so you get by omega m squared, roughly, maybe some 2s and so on. Okay? And now you can rewrite, remember what Jm was. Jm was integral of xm with j. So you can rewrite this as integral of j of sigma prime, x of sigma prime. There are probably some square root g's thrown into place. Okay? xm divided by omega m squared. Is what you get by completing the square. E to the power, that's right. e to the power plus minus some minus signs. No, not doing that yet. So you get e to the power something like this. Now you see that this you can write as an integral e to the power something. J of sigma prime times the Green's function, sigma minus sigma. But now we have a precise definition. The precise definition of the Green's function is xm of sigma prime over omega n squared. Now let's see what we get when we take del square on this. If we take del square on this, that cancels the omega n squared and almost gives us a delta function by completeness. But not quite, because that term doesn't have the x0 squared. Okay? So the Green's function really obeys the equation. Del square on G is equal to delta function exactly minus x0 squared. This is just a constant. Remember, x0 is just a constant. Okay, and if you keep a careful track of your square root g's, you get some square root g's, you get a 1 over square root g. If you do it carefully, keep it track. Basically, because del square has a 1 over square root g. Okay. Sorry, you get 1 over square root g there. Right? Del square there. Behind this. We can do it more carefully. Not more. Okay. Alright. So this gives you the precise definition of the Green's function. This is the Green's function with which you should do working. A Green's function that obeys this equation. Okay. Now there's a physical interpretation of this x0 squared. Can somebody tell me? I'm claiming that if you were really working on the sphere or any compact manifold, and we did this, we had this equation without x0 squared, there would be no solution to the equation. What?
Yeah, it's like a
background charge. Yes. But now can you tell me mathematically first, why if we didn't have x0 squared, this equation is impossible to solve? Suppose we had an equation with this on a compact manifold. I'm claiming there's no solution to that equation. Why?
Point charge in a compact.
Completely right. It's like potential of a point charge, of a single charge compact manifold. Just mathematically you take the equation and integrate it. Because the total derivative on the left hand side gives you 0. Here it doesn't give you 0. And in fact this x0 square is carefully chosen. It's a constant term such that this integral will cancel this. Okay, I mean, square root g times x0 square integrates to 1. That gives the delta function. Okay, so what the electrostatic problem that we're really solving is the potential of a point charge somewhere and a uniformly distributed negative charge around the rest of the space, so as to allow Gauss's law to be created. So as to allow a solution consistent with Gauss's law. So now we really find the Green's function on the plane. Now we can work in our z coordinates. We know what equation we really have to solve. Okay? So you can honestly now find the Green's function that obeys this. It has a piece we worked with, it's a log, but it has an extra piece coming from this x. However, now if you go through the whole calculation that we did before, including this extra piece, you will find because of momentum, this is essentially a constant term. Okay? And you'll find that this constant term couples only to the couples to the ki's, and because in the end all ki's must sum to 0, this constant term drops. Okay, I'm going to leave it to you as an exercise. Try to redo the calculation we did at the beginning of the class. And maybe I should just write down the correct Green's function. That's very trivial. Okay, remember that del squared is equal to 1 by square root g, and then del squared. Suppose your metric is g alpha beta e to the power 2 pi times delta alpha beta. Then the square root g times the g upper here, which both are cancelled. So you get del squared in the flat plane times 1 by square root g, which is e to the power minus 5 times del squared. Times del squared on the plane, flat del squared. Okay? So the equation we want to solve is this is equal to e to the power minus 5 delta function. Okay? Minus x0 squared, which remember is a constant. So we want to solve the equation del squared is equal to delta function plus e to the power 5 x0 squared. Have I messed up? Sorry, there's a 2 5. Okay? Now, we know how to solve the first guy. That's the log we've been dealing with. So the solution is minus alpha prime by 2 log of z minus z 1 squared. But then you also got to solve the second guy. That's really easy because this is a constant. We know this Green's function. So all you have to do is to integrate e to the power 25 times x naught squared times minus alpha prime of phi of sigma prime alpha prime by 2 log of z minus z prime. So now if we take del square of this, we get a delta function, and we get this delta function integrated over this. It just gives us this. The delta function gives us okay, so that's the real Green's function. Okay, but now if you go redo the calculation that we did using this Green's function, I want you to go and check that none of this nonsense matters. Because of momentum conservation, every term that you get from here in the end drops out of the final terms. Okay, so that everything that we did at the beginning of the class was actually correct, though we weren't being very careful. Okay, there's one last thing I want to say. We spent a whole lecture on correlation functions with free scalar, and it's a little much. But okay, let's move. So, there's one last thing I wanted to say about doing things correctly, and that's this. You see, if we weren't using conformal field theory and conformal normal ordering, then there's another step in the thing that we did at the beginning of the class that's questioned. And that step is ignoring the sense contradictions. You see, what we should do is to honestly regulate and then renormalize the theory. Okay? So, let's see. So, suppose we were, in some sense, put the theory on a lattice. Okay? So, what does it mean to regulate the theory? What it would mean to regulate the theory effectively would be to take the 2-point function of the theory and to replace it by something that looks like the same 2-point function long distances, but is different at short distances so that it doesn't blow up. Okay? So, the 2-point function of our theory was log of z1 minus z1 the whole thing squared minus alpha prime by 2. This thing blows up at short distances. So you might be very tempted to say that this is equal to, so g is equal to this when z minus z1 is greater than epsilon and is equal to minus alpha prime by 2 log of epsilon squared for z minus z1 less than epsilon. Or you could do something more smooth. But morally speaking, you might be tempted to say this. Okay, as a way of giving a regulator, we still have to renormalize. First, just regulating your theory, you might be tempted to say this. I'm claiming that if you did exactly this, you would be doing a very bad thing. You'd be violating something sacrosanct. Can you tell me what? Well, yes, in a way, yes, you're right. But in some sense, from the point of view of the underlying theory, it's something even worse. Remember what the metric was in our system. The metric was this, was P del power 5 delta alpha. And we are putting a cutoff in coordinate distance. Yeah. Okay. So we're violating diffeomorphism. The right way to put the cutoff is with the e to the power 5. That is an acceptable that would be then a diffeomorphically invariant. Okay? So this and then would be log of okay, and then what would we have to say? We would have to say that is it was equal to then it becomes the value that z minus z1 becomes at this bound, which is so when e to the power 2 z minus z1 is less than equal to epsilon, we get instead z minus z1 times, so epsilon times e to the power minus 2 phi. Okay, you want to add epsilon, this thing to be very fine. You don't want to jump. Okay. Now, once we've done this, we can then renormalize our operators. We can then renormalize our operators by removing the appropriate powers of epsilon. Okay? So every operator, every self-contraction will give us an e to the power minus alpha prime by 2 k1 squared. That's really the anomalous dimension of the operator. This alpha prime k1 squared. So we define the true operator with the appropriate power of alpha prime. We define the true with the appropriate power of epsilon. That removes this epsilon dependence. But what we're left with is this phi dependence. Okay? So the net result is that every insertion of an operator gives rise to phi dependence. Okay? Every insertion of an operator gives rise to phi dependence. And let's calculate the phi dependence carefully. Okay? That phi dependence is what? The phi dependence was we had, remember, an e to the power minus ki squared by 2, and then we had ki squared by 2 times this 2-point function. So we had minus alpha prime by 2, and then we get a minus 2 phi. Sorry, minus 1. Yeah, minus 2 phi. Square way?
Okay, this should be z minus z1's mod square, right?
You're right.
And
This was square. Right.
no, and this the down is also square.
Let's call this epsilon square.
Yes.
Okay? So we've got this e to the power, we've got this dependence each term. Now let's see. We have an e to the power minus, therefore what we get? We get e to the power minus ki squared phi by 2 with an alpha. Okay? So for every e to the power ikx, we get some phi dependence. But remember that if we were doing things correctly, our vertex operators also have this insertion. Our vertex operators also have this insertion of square root g. So we will add a square root g times e to the power I k dot x. Integrator of the whole worksheet. Okay? This object transforms like e to the power 2 phi. So if we were looking at tachyon vertex operators, to get rid of a phi dependence, we need this object to transform like e to the power minus 2 phi. When would that work? That would work if ki squared, alpha prime ki ki squared by 4 over e to the 1. So it's precisely the mass shell condition for the tank. So, the net conclusion, and this is an important physical conclusion, is that if you did the path integral just in an honest way, regulating it in a diffeomorphically invariant way, defining your operator in a diffeomorphically invariant way. By that I mean you're allowed to remove powers of epsilon defined value invariant length, not by then you find that you get wild independence from renormalization of the operator, which precisely cancels the wild dependence of the renormalization that comes from explicit factors of the metric if you are exactly on Marshall. Okay? You remember lecture 2 ago I promised you that I would give you a better, a more physical way of understanding why the vertex operators have to be 1-1. This is essentially that point. You see, it's the fact that this vertex operator really has scale dimension 1 that was the heart of the this phi dependence appearing when you renormalized it. Okay, of course not. It doesn't have to appear through renormalization. It could happen just automatically. You see, when we have the vertex operator del x times e to the pi k phi, then k square, the Marshall conditions k square is equal to 0. So we get no contribution from renormalization. But in that case, the vertex operator is itself classically wild because there's square root g and then there are 2 dels. Okay? But in every case, the vertex operator must just honestly be 1-1. So the sum of all e to the power 5 factors that come from classical contributions plus from quantum contributions have to be equal, have to add up so as to cancel the vertex, the e to the power 5 dependence square root g. And you see how that works if you do it honestly. Okay? Fine. So I think this is all I wanted to say about correlation functions with the free scalar field. Kulchinsky, as usual, has a very beautiful discussion of all of this at the beginning of chapter 1. Can I take 5-10 more minutes to talk about the correlation functions of BC system? Then in the next class we'll really be ready to get into the correlation system. There'll be no calculation. Okay.
It's 5-10 minutes?
Maybe 15 minutes.
So you continue.
Yeah. Okay. Okay.